I start?
Hold on 1 second. All right. I'll briefly introduce you then. Yeah. Hi everyone. Thanks for dialing in. Despite some issues with the listserv, glad that all of you at least got the email. So we have another very exciting presentation this time from Lingzhi Sun at the University of Hawaii, and Lingzhi is going to be talking to us today about some recently published work on using polarized infrared spectroscopy to characterize adsorbed and internal water. So just a reminder to everyone, if you're not talking, please make sure that you're on mute. And Linja, if people have questions, do you want them to wait until the end or ask in between? I know either is fine, but I know people have
Yeah,
different
yeah,
preferences.
you can do anyway because we have a smaller group. So I feel like if you have a question, just go ahead and ask at the slide, so can just solve it right after.
Mhm. All right, sounds good. So with that, I will let Linja introduce herself in more detail if she wishes. And yeah, take it away, Linja, whenever you're ready.
Okay, thanks, Percy, for inviting me do this presentation. So if any of you are interested, so I just went through an earthquake thing in Hawaii last week, like basically right before the Chinese New Year. But the earthquake center wasn't near us, so but the shaking feeling was kind of scary. But so I'll start introduce the talk today. So we use the polarized spectroscopy to characterize the surface adsorbed and internal water in planetary materials. I want to move this floating thing. Okay. So this is a a collaboration between me, Paul, and my friend Lilia Fisher. Now I cannot. Okay. So a little bit introduction. So water on planetary surfaces have multiple origins, and because of these different origins, they might present as different formats in planetary materials. For example, if it's pyroclastic deposit originated, they might carry this metal water trapped within the glass beads, and that ends the internal water. And if it's just a surface anhydrous mineral broken from anhydrous rock, it's more likely they will carry this surface adsorbed water, possibly from the transient exosphere. So currently, there is no available method to distinguish these two kinds of water. So we got inspired by polarization. So let's start with a little bit of theory. So if you can, hopefully you can see my mouse moving. So
Yep.
yeah, that's great. If a beam of light that's unpolarized shine on the planetary surfaces that's full of grains, most of the light will be reflected off the surface. And these are the perpendicularly polarized light. And I mean, by perpendicular, I mean its oscillation of the photon is perpendicular to this flat surface we're seeing, like this plane defined by this light source, observer, and the target. And also some of the light will go transmit into the grains, then got multiply reflected, refracted, and transmitted. And these are the volume scattered part. And because of this multiple scattering thing, the polarization kind of will get lost due to this so many interaction. And we will consider this part contains half of perpendicular and half of parallel. And the parallel is oscillating like parallel to this plane. So when we observing the light from the surface, was observing from two directions. So from the perpendicular branch, you will see most of the surface reflected light and a small part of the volume scattered part. So it's dominated by the surface reflected part. And we're looking at the parallel branch, it only contributes from the volume scattering part. So these are the part that contains internal water from the internal of the grains. But the perpendicular doesn't contain that much from here. And so we tried many samples, but eventually we decided these two. So we were trying to test material with internal water and without internal water. So for material without internal water, we selected calcium fluoride. It's an infrared optical window designed for 3-micron measurements, and that is for sure to have no detectable water absorption. And here I have a transmission spectrum that goes from about 500 nanometer to 1600. You can see that around the water absorption area, there is no absorption feature. And another one is Opal A, which is a well-known gem that contains a lot of internal water. So it's both internal structural water and surface adsorbed water for this material. But because the water content is a bit too high, it can be like around 3 to 15%. So we diluted this sample with the calcium fluoride sample by adding like 90% of calcium fluoride. So another reason that we choose this two sample is because their albedo are similar, which will eliminate any difference caused by the difference of polarization degree. And here are the samples we prepared. So we have the calcium fluoride on the top row and opal on the bottom row. So we prepared them at 5 different grain sizes. Excuse me. This is because we wanted to test the idea proposed by Lily Fisher that water absorbing properties are affected by the surface area to volume ratio, which is the grain size variation. So for each sample, we crushed them into powder, then wet sieved them into 5 grain sizes. This grain size labeled here is the midpoint of the 2 end sieve size. And here is the experimental setup we have. So the instrument we're using is this white box here. It's a DMP brand FTR spectrometer. And we add a polarizer in front of the lens here. And then here's the light source. We used a sandblast aluminum plate and standard. We didn't use the gold because it's highly specularly polarized, which isn't good. That's too much for our sample. Then we determined the maximum and minimum polarization position because this is a wheel. So spin it and read the numbers on the instrument and see when it's the maximum polarization that's corresponding to the perpendicular polarization, and the minimum is corresponding to the parallel polarization position. And we have this sample stage, which is a black body. So it can heat up at 100 C steadily when it's on, and when it's off, it's a cold stage at room temperature. And our lab is pretty cold. It's around like 20 C. And here is a schematic diagram of the light path from light source to the instrument.
Hey, Lingzhi, quick question. The light source, is that a polarized source or the light source is
No,
unpolarized?
no, it's not a polarized source.
Oh,
You have to have your light source unpolarized.
Mhm.
But there is some instrumental polarization involved in there. But because we were measuring the, let me see, because I think I have measured the instrument polarization, but it's not very high. But
Oh,
that's a good question. You have to consider the instrumental polarization when measuring samples. And so to get the data, firstly, we heated the samples. We're trying to remove most of the surface absorbed water to start with a very low water level, but we don't have a purged box or something, so just like heating it in the air. And here is our scientific heating plate. So we just leave all the samples and the aluminum standard for heat there for calcium fluoride. We heated them at 100 C for 12 hours, and for opal, we heated them at 280 C for 24 hours because it has more water involved. Then while it's still heating, we measured the polarized hot spectra by putting it on this hot plate at 100 C. Then after we measure the hot spectra, we leave the samples and center together in an ambient environment for 12 hours. So it cools down and atmospheric water will absorb to the surface. Then we measure the polarized cold spectra. So for each sample, we have hot spectra, cold spectra, perpendicular, and polar and parallel. So 4 spectra for each sample. And we derive the reflectance by using sample subtracting dark versus standard subtracting dark. And here are the spectra we finally derived. So the top panel is 6R for calcium fluoride, and the bottom panel, these are for opal. And if you look at vertically, the first column is perpendicular branch, and the second column is the parallel branch. And I'll introduce this one later. So we observed some similarities, and also like for each panel, the top row is hot and the second row is cold, and it's same for opal. So when we look at the cold spectra compared to the hot, you will see that the cold spectra has stronger absorption depths compared to the hot for both opal and calcium fluoride. That's corresponding to the absorption of surface water from the atmosphere. And also the parallel branch has stronger absorption depths than the perpendicular. Look at this column compared to this one. And then there's also a tiny absorption for calcium fluorides, like this tiny absorption near 3.4, 3.5, but for opal, it's kind of like a wider absorption feature here, which is highly possible organic vibration. And there are also some differences between these two samples. One has internal water and one does not. So the 3-micron absorption depths for calcium fluoride is much weaker than opal because it only has surface water, and opal has a lot of internal water. And the variation of the 3-micron absorption depths with grain size is very different. So for calcium fluoride, so I use the same color scale for both samples. So purple, blue, greenish are the smaller grain size, and red, orange are the larger grain size. You can see that for calcium fluoride, all of these spectra, the orange and red sample, the larger grain sizes have smaller 3-micron absorption, but the smaller grain sizes have stronger absorption 3-micron. But if you look at the opal sample, it's the opposite. the smaller grain sizes have smaller absorption depths, and the larger grain size have stronger absorption depths. And also, for opal, we see this absorption near 2.223, and also there is this 2.75 hydroxyl absorption, which might be more obvious in this one. And another thing which is quite interesting we observed is the ratio spectra. So it's a ratio of parallel and perpendicular branches. You know, when we get the spectral, just like playing around with it, just trying to see what we can get from this result. So I just made a ratio plot between these two branches. And then you can see it, the ratio plot for calcium fluoride on the very right, and for opal is also here. So compare for calcium fluoride, if you look at the ratio spectra, comparing to the two polarized branches, there's a very obvious difference that the grain size variation between the large and small size fractions seems minimized, except for this very large grain size. It's over 100 microns. That the rest of them are pretty much showing the same amount of 3-micron absorption depths. But still, if you compare the hot and cold spectra, you can see this increase in 3-micron. So it's still sensitive to the water absorption increase. But for opal, it's quite different. This 3-micron depths sort of increase with grain size but still the cold have stronger absorption than the hot. And also in this ratio spectra, that organic absorption at 3.4 and 5 sort of disappeared. So it kind of suppresses the organic absorption. And also for the opal too, it's much narrower if you compare to this to the polarized branches. And also the 2.75 micron absorption is kind of disappeared too. So to quantify this absorption feature, this grain size variation, so we wanted to apply MGM analysis to it. But before that, we need to determine the input water absorption feature, the input parameter for that. So we mixed the spectrum of OH and H2O spectrum, then generated this series of mixture between them. So for OH, it's from this Takir work. They measured the infrared spectra for this meteorite. And they also have this 6-micron absorption feature. There is 0 6-micron absorption feature, meaning there's no molecular water in this meteorite. They were measuring in vacuum. So this kind of odd spectra is the OH, and this bottom blue spectra is the H2O. So H2O is directly modeled from the optical constants from this Hill and Curry work, but we were modeling it using a very thin coating of water on plagioclase grain. Then we applied MGM to these water mixtures. So from these are the MGM input analysis results. So we have this pure OH, which have this 2.78 and 2.99, which is 3-micron absorption feature. And the pure water have 2.9, 3.1 absorption feature. When we mix them together and these two panel, you'll see there will be a 2.76 and 2.9 and 3.1 feature. So considering that our spectrum might have both. So our input feature is this 2.75, 2.9, 3.1. And we think that 2.75 is indicative for the OH band, which is a pretty much well-known selenol structure between silicon and OH. And the 2.9 and 3.1 is the water vibration bands. So here are some example MGM analysis results for calcium fluoride and opal sample. For calcium fluoride, basically have no 2.75 because there's no silicon. It only have this two water band. So here's some example for perpendicular hot, perpendicular cold, and parallel hot and cold. And for opal, it's more complicated because like it have this kind of wide 3.4 feature, and we also added some extra features to minimize the error between the modeled and the measured spectra. So I have three water-related absorptions, these 2.75, 2.9, 3.1. So it's the same position absorption center for each spectra. And here are the parameters, the center width and strength of this 2.9, 3.1 absorption feature versus grain size variation. So for calcium fluoride, again, it's this 2.9, 3.1, that's only atmospheric water absorbed to the surface. And the widths have this kind of slightly decreasing trend, but not very obvious. And the strengths show pretty obvious, not very obvious trend. But if you look at, so the cold are blue, hot are red, and the filled circles and triangles are perpendicular, parallel, and the open ones are perpendicular. If you compare to the blue and the red symbols, like the cold always have stronger strengths compared to the hot, and the parallel, which contains the volume scattering part, always have stronger absorption than the perpendicular. And with grain size variation, we can see that they kind of fall into two groups. So the smaller grain size fractions have a stronger absorption than this larger size fractions. And for opal sample, it has an actual band at 2.75, but its width or strength doesn't vary very strongly with grain size variation. But for 2.9, 3.1, the water band, when the grain size is smaller than 100, you will see this kind of increasing trend for all branches, hot and cold, this grain size. So it's the same for these two absorption bands. But when grain size is larger than 100, the variations kind of show a decreasing trend. That's kind of odd. And also it's the same when grain size is smaller 100, the cold sample have stronger absorption than the hot. We then measured the ratio spectra. We analyzed it with MGM, and it only showed us one strong 2.9 band. So still the cold are blue, hot are red, and opal are circle, and calcium fluoride are diamond. And you can see with grain size variation, this ratio spectra show basically no variation along grain size for calcium fluoride, which means like the grain size effect is basically minimized. And using this, we can measure, if we know there's no internal water for some planetary surface material, we can use this ratio polarized spectra to measure the water content. And for opal sample, you can see this kind of increasing trend when grain size is less than 100. So the 3-micron strength increases with grain size, but when it's larger than 100, kind of decreases with grain size. And also, the cold samples have stronger absorption than the hot, which means this ratio spectra is sensitive to surface water absorption. And so here are some major takeaway points. Firstly, cold samples show stronger water absorption than hot samples, which indicate the absorption of atmospheric water. And the parallel branch have stronger water absorption than perpendicular branch, indicating that the volume scattering can detect more water than surface reflection. When grain size is smaller than 100 microns, the absorption strength of polarized spectra is closely related to grain size variation. But when their material has internal water and without internal water, the trend, the 3-micron variation trend with grain size is opposite. Because when there is no internal water, it will be this strict relation with surface area to volume ratio as proposed by Lily Fisher. But when there is internal water, the volume scattering will carry a lot of water from interacting within the grain at longer light paths. And the ratio spectra, which shows no grain size dependence for a calcium fluoride sample, but it has a strong grain size dependence for opal sample. And we will further study this and try to quantify the relation between the absorption depth variation with grain size. And this method will be promising for detecting water on planetary surfaces if we know the grain size. And that's all I have for today, and I'm happy to take questions.
Awesome. Thanks, Linda. This is really interesting, and it's also like a really complicated problem. I mean, just trying to make sense of it. So yeah, so thank you for presenting. All right, so what questions do we have for Linda? So feel free to, since it's a small group, feel free to unmute, or you can put something in the chat or raise a hand if that's easier.
Hi, this is Licia. Great talk, Lingzhi. This is super interesting. Could you share a little bit more about how you can port these results over to figuring out hydration on the moon?
Wait, sorry, can you repeat that question?
Could you share a little bit more about how you plan to use these results to investigate hydration on the moon?
Okay, so there's no satellite data right now because there's only PolCam, which has polarized spectral data for the moon, but they don't span 2-3 micron, so we cannot use that. Well, the only possibility we can do is to use terrestrial telescope to add a polarizer in front of it, but there's strong atmosphere stuff in there. So like maybe we can try fixed micron for now, but fixed micron is hard to get to measure in lab right now because it's highly saturated. But we are thinking about building a perch box to measure that, then apply to telescope data. Then we can try to look at some surfaces at paraclastic deposit on the near side and those areas that don't have paraclast deposit and see if we can see anything.
Okay, thank you.
Yeah, no problem.
Well, that's really cool. So so you think you could maybe get some ground-based observations that
Yeah, that's what we were
Nice.
hoping.
Awesome. What else? I guess I'll ask one while people are thinking of more questions. So like so near the beginning, you had that nice schematic showing the
Oh
surface
yeah.
scattering and the volume scattering. So like I guess one question is it, yeah, so is it trying to think how to ask this, but is it really picking up the difference between adsorbed versus internal water, or are you also sensitive to differences in hydration with depth? So, so I guess there's some penetration
You mean
depth,
for
but is
the
the
surface reflection? Like
yeah. So
for this
the
reflection,
mhm.
it will be like 1 bounce from surface
Uh-huh.
observer.
Okay.
But the others will go in and explore something under the surface. So this top 1 bounce photons are the most strong part
Uh-huh.
in the observed light.
So those would really sort of be seeing like the water adsorbed to the top grain, and the other stuff would be seeing.
Yeah, because like this perpendicular branch contains some of this internal water, like internal multiple volume scattering. But the thing is, it's too strong. This won't have a strong effect. Even like it has some like imagine this is like 1% compared to 90%. It will be heavily diluted, even if it has some information. But the parallel branch is just pure, this volume scattering. It's not diluted.
Hmm. And would the perpendicular be sensitive? So in some of the samples, like if you have hydrogen implantation in sort of like the rim of a grain, you might have sort of a, a like a implanted OH very close to the surface of the grain. Would the perpendicular be sensitive to that? Or would it really only detect like water that's on the outside of the grain, not just OH that might be just,
Okay, so
implanted at a
you're
very shallow
saying
depth?
there's like some water bouncing around in here.
No, I mean, so the in some of the if you have solar wind hydrogen that's being implanted, like is it possible that it can be implanted sort of at like at the very rim of the grain? And
Yeah.
would the perpendicular be sensitive to that, or is it really only picking up what is outside the grain and adsorbed?
If it's on the grain or near here, it should be sensitive to that,
Hmm.
I think.
Okay. Right. More questions. What else do people want to know?
Well, this is Leslie Gertz at Missouri University of Science and Technology. How precisely does the grain size distribution need to be characterized in order to use this?
So the grain size we have is these. So, but basically we were kind of, our results show this smaller groups and larger groups, like it's not that sensitive. So you don't like, I guess the grain size variation can be like fine and coarse, then it will be able to pick up the difference.
Okay, so it wouldn't need necessarily up close physical geotechnical sensing of the site or representative regolith of the site in order to use this. You could get that from, say, radar or something like that.
Mm, what's I don't know actually. Yeah. So for when we're using the excuse me. So for the calcium fluoride, if you're using the ratio spectra, you don't have to know the grain size because it's the same for all grain size. But for when there's internal water involved, you might want to know a sort of accurate grain size variation. But at the same time, polarization at the visible near infrared, it's able to detect grain size variation. Then there are works like using polarized near infrared spectra to derive the grain size. So they can get things at a relatively high resolution and high.
Okay.
Yeah.
Oh, I see. Thank you.
Yeah.
So I have a kind of a general question. So what do you think is next in terms of this? Like, do you think you'll move straight to trying to compare this to observations, or yeah, or like, maybe experiments on lunar samples or other kinds of parameters? Like, what do you think is the most important next step in terms of taking this forward?
So what I'm thinking is to send these samples to measure their water content using the program desorption. What's that called? I always lost the
TPD, temperature program
the
desorption?
program desorption, yes. So I can sort of quantify the water content with the spectral feature. Then we're gonna try to measure more samples and see, like, to test on, because this is only for like this two samples pretty unique and sort of not quite related to lunar materials. So we want to get closer to lunar related stuff like these anhydrous minerals, all of them plagioclase, like that. I really wish if we can get some lunar samples. Because I know, like, we measured, Paul and I measured the water content of the newly opened Apollo 17 core 73001. And so we just put a DMP, like it's the same instrument. We put this instrument inside the glove box at the GSC, and there's no absorption. That sample has no water in there. And Paul has a poster about that at LPSC. So if we can get that sample and measure the polarized spectra, that will be exciting. But I don't know, like acquiring samples is like really hard and it's pretty precious. I don't know if they want us to play around with it. But if we can, that would be very awesome.
Cool. Yeah, no, that sounds really promising. And Rosemary Killen has a question in the chat. And Rosemary, feel free to unmute as well. But Rosemary asks, would it help to put a telescope on the ISS or an orbiting platform? I guess that's for
Yes, yes.
polarimetric
Oh
measurements.
yeah. Or like the retiring Sophia. Yeah, that would be very helpful, but I don't know if we're able to do that. But that's a very genius idea.
All right. And I guess related to Sophia, so you mentioned that it's harder to do this at 6 microns?
For terrestrial, because there's so
Oh,
many,
okay.
it's so easy to saturate, but if in vacuum, it won't. So we were thinking about measuring that 6 micron by building a purged box. So that's the next step.
What is a a purge box? So like so
Like
you
it
would sort
can
of evacuate the
suck all of the that
okay.
away.
Okay.
So we can sort of measure in a very dry environment.
Interesting. So not vacuum, but you would just
Vacuum,
take
yeah.
the
Vacuum
okay.
will be good, but we're still thinking that we do have a vacuum, a little bit of vacuum thing in
Mhm.
here. So there are many ways to do this.
Interesting. Do we have more questions? Sometimes if you wait until the silence becomes uncomfortable, then people will ask a question.
If anyone is interested in volcanoes, like since that earthquake happened, there might be a new eruption on Big Island. So if you want to travel here and watch the lava flow, that will be very exciting.
Ah, so that's like triggered by the
Yeah,
earthquake?
like earthquake is very pretty much related to volcanoes, usually.
Yeah, especially in Hawaii.
Yep.
All right. Well, if no one has any questions, we still have a few minutes. So I know LPSC is still a few weeks away, but do people have LPSC presentations or talks or posters that they'd like to mention while we have everyone here? I know I was looking at the program, so I know there's at least a few sessions on lunar volatiles and some other cool stuff too.
I have a poster on the exosphere created by degassing from all kinds of anthropogenic sources like rovers, airlocks, backpacks, the Starship, things like that. You know, a lot of them degas water, oxygen, nitrogen, and trash. Trash is interesting. Yeah, so yeah, take a look at my poster. I'd like to know what people think.
Yeah. Anyone else have things to present at LPSC? Lingzhi, did you say you were presenting this at LPSC or was it something different?
I have. So this work was a poster last year because I wasn't ready to give a talk for that. And this year I do have a talk. It's on Thursday under the lunar mantle session. It's not related to volatile though. So I just mapped the magnesium number of the SPA area and at the potential mantle exposures near there. And one of the pretty exciting thing I saw is the next China Chang'e 6.
Mm-hmm.
I lost
7? Yeah.
the next sample return mission gonna land near Apollo Basin, right? And I found there's a lot of mantle exposures near their landing target area. So they might be able to return the first unambiguous mantle material. And that's pretty exciting.
Wow.
Yeah. Nice. What about
I got something. Yeah,
go ahead.
I think I'm in the volatile session, but it's a talk on radar brightness of some of the craters in the Viper landing area. I'm working on the PSRs of them right now, so if I can get that done by LPSC, we may have some volatile related stuff, but tentatively it'll be both the craters and the PSRs if I can get it done. So
Nice. Yeah, that sounds exciting. What about Ziyu, Alicia, Cesare, Dave? Any LPSC presentations? Okay. Cesare is missing LPSC 2 this year. Okay, so yeah, I'm not the only one. Oh, Dave says he can't unmute. Let me see if I can unmute you, Dave. Yeah, I'm not sure what's going on there. But yeah, I know Dave has been doing some polarimetric measurements as well at APL. Not of the 3 micron band, I think, but yeah.
Yeah, I won't be at LPSC in person either, so I'm gonna try to do an interactive poster. So we'll see how that works.
All right. Yeah, Dave is being silenced, unfortunately. But yeah, Dave, yes, sorry about that. I have no idea I promise I'm not doing it deliberately. But yeah, but we recorded the talk, so so yeah, it'll be online. All right, any other questions or for Linja or news and views? All right, Dave says he has a poster on Lunar Vertex and the camera that he's developing under DALL-E. Awesome. Yeah, I guess other news of interest. I don't know if folks had any impressions from the league meeting yesterday. So there was a short presentation about Lexo, which is the successor to LRO that's currently sort of in pre-phase A studies. So there was a short Noah Petro gave a short presentation about that, and so I think it seems to be still in very early stages, but but I think there's a strong interest in doing volatiles related measurements as part of that. I think the details are still very much to be determined, but yeah, and what
A
else?
quick
I
question on
guess
that. On the
yeah.
Lexo orbiter, have they begun selecting instruments or at least deciding what's going to be on there?
They have not is my impression. So basically the way I understood it, so NASA headquarters has, they recognize the need for a follow-on to LRO, and so they've asked Goddard to just scope out one potential view or one potential option for what that might look like. So in order to do kind of cost estimates and things, they've made some choices about what kind of instruments they're considering. But someone had asked, so because the concept study is considering a laser altimeter, does that mean there's definitely going to be a laser altimeter on board? And the answer was no. So I think like the instrument types are definitely not final, and I think they might change. And the teams haven't been selected. I mean, so the teams will be competed. And I think even the instrument types are not set in stone. So they're making some assumptions about what instrument types might be on board so that they can come up with an estimate of how much it'll cost and so on. But I think, yeah, it looks like it's all going to be competed, and hopefully there will be lots of opportunities for people to get involved.
Okay, so it's like a reference design that they can use to actually put out a thing that folks can compete for.
Mm-hmm. Right. Yeah. That's a good way to describe it. Yeah, that's exactly what it is.
Okay. Awesome.
But
Thanks.
even though there's a reference design, it seems like even like if the reference design includes like certain types of instruments, that doesn't necessarily mean that when it's selected, it'll include those same instrument types. So I think what Noah was saying was, Goddard will provide this information to NASA headquarters, and the other sort of important thing that they have to draw on is the ClockSat report, which was sort of a league report on what a continuous lunar orbital presence would look like. And so I think headquarters will kind of take this Lexo study and the ClockSat, and then they'll decide what to do with it all.
Okay, makes sense.
Mm-hmm. Yeah. All right. Well, if there's no other news or questions for Linja, then
Well, I
I'll
just
give
have a
yeah
comment.
Rosemary. Mhm.
I was pleasantly surprised to hear that there's a call for work on sustainability at the moon. I haven't actually read the call yet, but yeah, I think they'll be interested in doing that.
Yeah, that was interesting. And in case folks haven't seen this, I will let me find the link and put it in the chat. But this is basically it's a new solicitation in Roses, which is sort of like, the annual list of NASA proposals. And so there's a call for interdisciplinary proposals on economic, social, and policy analyses of lunar surface sustainability. And so I glanced through the call, and so one of the interesting things is that they do reference things like where did I see this? Right. So they do mention things like protecting critical areas for scientific investigation, like the permanently shattered regions, maybe. And so that looks like kind of an interesting opportunity that might have some overlap with the kinds of research that folks do. So yeah, something that's new and yeah, good to be aware of.
Yeah, there's a session at the IAC on lunar sustainability, but it's very expensive to go there. It's somewhere in Europe, but if anybody has a lot of travel money, yeah, they have sessions on sustainability, which I find interesting that it's a topic that is kind of gaining interest.
Mm-hmm.
What
Yeah,
means
it's
that?
good to see it gaining
sorry.
interest in. Oh, sorry, I interrupted someone.
No, what's that? This meeting, IAC, you say?
The International Astronautical Conference, I believe. I can send you the
Okay.
link if you're interested.
Yeah, actually, I
Okay.
think that's in Milan, Cesare. It might be in Europe. I mean,
you
in
might be
Italy.
interested,
Wow.
Cesare. It cost like $1,000 for the registration fee, which
Wow.
kind of above my budget right now, but
Yeah.
Around summer, you said that?
yeah.
Okay, I will check that.
Yeah, I can send you the link, Cesare.
Yeah, it is. Right. Yeah, so it is in Milan and it is in I can't find when it is, but I guess Rosemary said summer. So sometime in the summer.
Yeah, I think so. I'll find the link.
October, I think.
Oh, October? Oh.
All right. Well, we're almost at the hour. So yeah, thanks again, Linja, for a great presentation. And yeah, thanks everyone for dialing in. Hopefully we will get the listserv fixed soon. But happy Valentine's Day. Take care. Safe travels to LPSC for those who are going. And happy March for anyone who's not going to LPSC. And yeah, we'll see each other again soon.
Can spring be far behind?
Yep, yeah, right around the corner.
Yeah. Thanks for
All
having
right.
me.
Take care, everyone.
Take care, everyone.
Bye-bye.
Bye.